So now when we talk of currents, we said we have basically two main types of currents. We said we have the direct current and we have the alternating current. Now with the direct current, we said that current flows through it in only one direction. We said that the other time. Now with alternating current changes periodically. The current in the alternating current, that of the alternating current changes periodically. So you can say an alternating current is the one which the current, or is the one which current changes periodically. And so when we say periodical, that means it changes with time. As time goes on, it changes with time. I hope you are getting it. So we can even plot this thing, a curve of that of a line, that of current against time. So it changes periodically. So at every time it is changing. Now, the electric currents that are normally produced by our generators are those we call the alternating current. The one we use at the Akusumo and the rest. And that is what we normally we tap at our homes. They are all produced by or generated by alternating current. And that current, it changes periodically. It changes with time. The electric current produced by an alternating current or generator increases to a maximum. So this it can, because it changes periodically, it can increase to a maximum and decrease to zero in one direction. In the other direction, it can increase to another maximum and also decrease again. And so it moves and it comes down. It moves and it comes down. Now, when you want to get the output of it or how it works, or let me say the output of it, when you look at it in one of the machines, the signal machines, you realize that it will give you that of a sinusoidal curve. And so, for instance, the output, when you have to look at the nature of it, its nature looks like that of a sinusoidal curve. Let me draw it well so that you get it. It alternates, it changes periodically. That means it changes with time. So if I have something like this, okay. So you are seeing that in this case, because it changes with time, there are instances it rises and it falls in the negatives. So it moves in the positive and it falls in the negative, or it comes to zero. So when you have something like this, it falls here, then it rises again, then it falls again, then and so on and so forth. So that from here to here will be one cycle, from here to here will be another cycle. From here to here, will be one cycle, from here to here will be another cycle, and so on and so forth. Now, from here, the peak of the current. So this will be the peak of the current because here we are talking about the current. I hope you can hear me, please. Yeah, we are talking about the peak of the current. So, hello. And so here will be current, and because it changes with time, against time. So if here is at time 0, the time is at time 0, we are saying that the current is at 0.2. Now, when it moves an inch, the current increases. When it gets to this point, the current falls and comes into the negatives. When it gets here, it comes to 0 and it falls into the negative. Then it comes again. So from here to here, when you do waves, you understand, you appreciate this curve well. That is why we do a lot of signals and so on and so forth. And so that is how, there's the nature. Unlike when you have a direct current, because it moves in only one direction, that is how it is. For the direct current, this is how the nature looks like. So this is how the nature looks like. This one, it moves only in one direction. This one moves only in one direction. But for this one, the alternating current, it alternates. That is why the name is alternating current. When we say it alternates, it fluctuates or it changes. That is why the ones we use at home, there are some instances, there are some days there's a fluctuation in power. There's some days, or most at times, there are normal fluctuations in powers and so on and so forth. And sometimes you realize that you have a high current, sometimes low current. It happens and so on and so forth, just because of the nature of the current, it is the nature of current produced. And so that is it. That we call it this thing, an alternating current. So in one cycle, you realize that part of the cycle is increasing, whilst some part is decreasing. Whilst in the second cycle, you realize that when it is increasing, some part will also come and decrease. So that is it. Now the alternating current and voltage, and we can also relate to this in terms of its voltage. So if it is voltage, it's the same curve, but this will be V and this will be T. That will be T. So and it has that of the sine curve or sinusoidal curve. That is it. Now the waveform is normally generated by a coil rotating with a constant angular velocity. And so what is done is the waveform. You see, there's the waveform of it. There's the waveform of it. There's the waveform of it. It is normally generated by a coil, which is rotating with an angular velocity. When we say angular velocity, the rate of change of angular displacement with respect to time. The rate of change of angular displacement with respect to time. And so that is it. And so the rate at which this changes with time. That is basically what we are talking about, the angular velocity. So in a uniform magnetic field. Now the current and the voltage at the time t is given respectively. You realize that this is at time t and this is the current. So here is the current. I've told you that, and here too is the time. Now looking at it, because this is a sine wave, and that means you have to be bringing the sines and so on and so forth, the sines and the cost and so on and so forth. So this one, the current for this will be that of because it is that of a sinusoidal current will now become current will be equal to I naught. No, I naught. Okay, so it will be I sine WT omega t. This is not just W, this is omega t. This is omega t. Where this omega is what we call the angular velocity. Angular velocity. That's the change of this displacement respect to time. You know, this displacement is angular. It is not like the normal flat one, like the linear velocity. This one is angular. You know, it is when you study circular motion, you get it. This is angular. This is not like the linear. If it was to be something like this, we would have been talking about linear. But here, the movement from this, the angular displacement respect to time. So that is it. So because of the angular nature, the current will be I naught. The I naught is the peak R. That means from here to here, the peak R. When you do waves, this we would have been talking about this in terms of amplitude. That means the height at which the current reaches. That is the I naught. The height at which the current reaches. That is the I naught. Hello, can you hear me?
Yes, sir.
Someone. So that is it. I hope I'm not rushing. Oh, I am.
So I think it's your connection is breaking.
Oh, okay. Sorry. Sorry. The network. So I should use proper network. Eh? That's what I used to teach you every day. So that is it. So that is it. So this one is the I naught. Now the I naught is the peak current. So if you have to consider this peak, then that means the peak current here is the I naught. The peak current here is the I naught. I naught. And it changes with respect to time. That's why we have the omega t. Omega t would have been talking in angles, but this one, because of the nature of it, we will just be talking about, we will relate the whole of this in terms of its angular velocity and time, because the whole of this constitutes the angular velocity. That means the rate at which it moves from here to this point with respect to time. Basically, that is it, or here to respect to time. So that is the current. So the current here will be I naught is equal to I naught sine omega t. And if you are to relate this in terms of earth voltage, so if for instance you are to relate in terms of the voltage with the same diagram, then that means here will be Vin values plotted against T. And so then that means here would also have been V naught. I don't want to draw two diagrams. So here would also have been V naught, which is the peak voltage. So now the voltage will now become.
Sir.
Yes.
Sir.
Yes.
Please, what is the symbol for the I naught?
The symbol for the
I naught. Yeah. Yeah.
What is the symbol? I don't know. I think that is the peak current.
Oh, okay.
The peak current. That means the peak. You can see this is the peak. It was to be in waves. Every time waves. It was to be in waves. We would have been talking about amplitude, the amplitude of the current. Are you getting it? So that is the height at which the current reaches or raises or increases to, and now comes and falls back. And so this one is the peak current. That is the I naught. Yeah, Bridget, ask a question. Bridget, your hand is raised. Please ask your question. So that is it. So our V2 will be V naught sine omega t. Our V2 will be V naught sine omega t. That is it. Now, where I told you that the I naught is the peak current and V naught will become our peak voltage. That means the amplitude of the voltage or the height at which the voltage reaches before it falls. Before it is thing, before guys, I'm coming, please. So we are talking about alternating current, and we said that with the alternating current, yeah, and a current, we said we have two main types of current. We said we have the direct current and we have the alternating current. Now we are done with direct current, and we said with the direct current, current moves in only one direction. Whereas in the alternating current, current changes periodically with respect to time, or changes periodically. Now when we say something changes periodically, then I'm trying to say that it changes with respect to time. So at every time, the current is changing. And so if you have to plot a graph of the current against time, you realize that at every time this thing is changing, the current is changing. It's either there's an increment in the current or there's a decrement or there's a decrease in the current. That is basically what I'm trying to say under the alternating current. And I said when you have to plug, if you want to know the output or the let me say the output of the current in terms of graph, when you the signal, how the signals appears and so on and so forth, it appears in a sinusoidal wave. Sinusoidal wave. Now when you do wave, there's how a sinusoidal wave looks like. A sine sinusoidal wave. That's how it looks like. And I said that because it changes periodically, at one point you realize that you see it to be increasing, or it increases at one point, whilst in another other point it falls to zero or decrease. That is basically what I've represented here. And I said that, so looking at this, then that means this, if you have to consider current against time, then this will be that of current against time. But the peak, when the current raises to this point, the peak, or when it reaches before it turns, is the peak of the current with respect to this point. Now when it gets here, this is also the peak of it. And so here we believe that they will definitely be equal. So if the peak, this is the peak, then this peak, the peak or the current at the peak is what we call the peak current, which is denoted by I naught, and given by sine omega t. And I saying that the omega t is angular velocity. Now, when we talk of angular velocity, you do when you do, I know those of us who have done circular motion, you should be able to understand angular velocity, the rate of change of what they call angular displacement with respect to time. Now, the reason here we are talking about angular is because it is not linear. If you are to be talking about the linear displacement, we would have been talking about just a normal straight line or something. But yet it's angular, like in an angular form. You understand? Like this, angular velocity in a circular form, semicircular form. That is basically what I'm trying to say. And so before you can be able to, instead of if it was to be some, like just something normal, we would have just used omega here. But here we are talking about the whole issue here. And so that means it's the I naught, the peak, not the current, the total current is the peak naught sine omega t. Now, if you are relating it in terms of velocity, that is basically the same thing is going to be. It will be v naught, which is the peak velocity, sine omega t. That is it. I hope you are all getting me. I just went over because some people didn't come early. So that is it. My network is disturbing today. Kindly forgive me. Kindly forgive me. So that is it. Now you bear with me that if under waves, those of us who have done waves, omega is also given by 2 pi all over t, where t is time or period. We all know this. How many of us don't know this equation? How many of us don't know this equation? So this equation, this is omega, angular distance. The angular velocity, we can also relate it in terms of 2 pi. You know, 2 pi, when we talk of circles or when we talk of circular something, we normally use 2 pi. So you should just know where it's coming from. And so omega is equal to 2 pi all over t. But we also know that t is equal to, period is also equal to 1 all over f. 1 all over f, which is frequency. So then now we can, anywhere we see t, we can put in 1 all over f. So we can get our omega now to be equal to, 2 pi f. Omega should be equal to 2 pi f. And so that is omega. Now, I said omega is the angular velocity. So anywhere we see omega, we can substitute that here. And so instead of the I is equal to I naught sine omega t, we can also get I is equal to sine 2 pi f t. Are we there? We can also get it in that way. We can also get this is I, the current. And we can also get a voltage or the potential difference in terms of the peak voltage sine 2 pi ft. So we can relate it in terms of this too. That is it. Now, I've already explained everything. Now, let's talk about, so we have the voltage, we have the current. We can relate them in terms of their resistance. We can relate them in terms of their power. Now, let's relate them in terms of their power. You know that I taught you that power is equal to current times voltage. That you already know. And so power is equal to P is equal to, so the power of this alternating current. So power is equal to, or the power generated by this alternating current, or from this alternating current and voltage vessel. So this is it. But because this power is from an alternating source or from a generator source, the power will now become, the I, we know I is equal to I naught sine 2 pi. I naught sine 2 pi. I naught sine 2 pi. So this will be I naught sine You can do it in terms of omega naught, omega t, or 2 pi ft, whichever way. Times v, which will be v naught sine. This will be v naught sine omega t. Yeah, please ask your question, Ruben. Ask your question.
So please, the V in the power in terms of current, is it please the V, does it stand for velocity?
V is voltage. V is voltage or potential difference. We are talking about this thing. V is potential difference. Why don't you hear when I was teaching power? So that is it. But when you get here, you know, mathematically we can multiply sign because this they are all equal, so we can multiply them. So we can get I naught V naught sine squared omega t. That will be our power. Do you get it? Do you get it? So that will be the power from an alternating source. An alternating source. Do we get it? So we said that because it is alternating, it changes periodically. So it changes with respect to time. So at every point in time, the current is changing or the voltage is changing. I hope you are getting to this point. And its output is that of a sinusoidal curve or wave or something. So this is how it looks like. And so to be able to get the current will be that of this sine, because it moves in a sinusoidal sine, the omega t, that means the angular velocity by t, because it works with time.
Sinusoidal.
Sinusoidal. Or I should spell it for you.
Yes, sir.
Sinusoidal is S-I, sinusoidal. Sinusoid. Sinu. There's it. So I hope we get it to this point. I've been able to explain the power and so on and so forth. Please, do we get it to that point?
Yes, sir.
If you don't understand, please let me go over so that, because between today and next week we have to finish this alternating thing. Then we are done electricity. So can I please clean the board? So now, can I please clean the board?
Yes. Yes, sir.
Yes.
Okay. So now we have that of the power. So the power is I naught, which is a peak current by peak voltage, sine squared omega t. Sine squared omega t. Sine squared omega t. The squared is affecting all of them, but that's why sine squared omega t. So in this case, this becomes the angle when we are talking about this. I've taught you, I don't know, you've done trig and so on and so forth, so you should know all this. Now we are done with what we call the power. We can also relate it in terms of the heat energy or energy, in terms of heat energy or energy. And so if H is the energy dissipated, if H is the energy, whether heat energy or anything, if H is the energy, and I is the instantaneous current, I is the instantaneous current. The instantaneous current. The current at the instance. Instantaneous current. The instantaneous current. And V will be our potential difference. Potential difference. Potential, please. Potential. Now, so if you have something like this, then that means already we know what our energy is in terms of this. You know, energy is given by, in terms of electricity, we studied all this. That's current times this times T. I hope you know this formula. How many of us don't know? Because I've taught you. So we already know this. So in terms of our calculation, we can, when we are using instantaneous current, we can use these calculations to do our energy, to calculate for our energy. Now let's talk about our root mean. Our root, now if you want to, you know that V is also equal to IR, so we can relate it and get I squared RT. This, all this I've taught you, Dada. All this I've taught you, Dada. So that will be I squared RT. All this I've taught you. Now let's do root mean square current and voltage. Root mean square current and voltage. Root mean square current and voltage. Yes, a little bit dicey, but I'll do my best to explain it to your understanding. Root mean square, listen. So root mean square into brackets R S current and voltage. Now you realize that in AC, both the values of the current and the voltage keep changing. That's we've already established this. So in an alternating current, both the values of the current and the voltage keeps changing with respect to time. Now, for practical purposes, it is normally advisable to obtain the effective value for both the current and the voltage. Practically, in practical ways, or yes, for practical purposes, it is normally advisable to obtain the effective value for both the current and the voltage. Or in talk of the effective, we are talking about the resultant value for both the current and the voltage. Now, the effective current is always or normally called the root mean square current. That means the effective current, or in terms, in something we can say the total current, is normally referred to us as the root mean square current, which we write as I subscript RMS. So root mean square current, that is effective current, and that of the voltage will be V RMS. And so for practicality purposes, it is normally advisable to obtain the effective value for both the current and the voltage. That means the total current and the total voltage. It is very distant. Now what we do is we express them in terms of root means, and so that of the current we call it the root mean square current, and that of the effective voltage we call it the root mean square voltage. And so that is it. That is it. So now the average value of the current. So what I was talking about, the effective current is normally given as root mean square current, and it is normally given by I. It is normally given by RMS. Now that of the voltage, EV, which is the effective voltage, it is given by VRMS. Now we are going to relate them in terms of their peak value and so on and so forth. We are going to find a relationship between the effective, what do you call it? The effective or the root mean square current and the peak current. We are going to relate them. Then we are going to do that for the voltage, and then we find a common denominator, a common constant. Then we use that in our subsequent calculations. We come and talk about the phasor diagram. When a class ends, you join again. We do the last section. We are coming to talk about phasor diagrams. We are also going to talk about the types of AC circuits. We are going to talk about the pure resistance circuit. We are going to talk about, that is a circuit made up of resistance. We are also going to talk about pure capacitor circuits. We are also going to talk about pure inductor circuit. Then we do the combination of AC circuit components. So we are going to do a combination of resistance and capacitors. We are going to do the various combinations. The resistance and inductor, when you combine, when you have a resistor, you have an inductor. When you combine them, we are going to do that. Then we are also going to do that, combine both all the three. And then I think we do power in an AC circuit. Then we do transformers. Then we are done. And so that is it. Let's just manage and do it. So the average value of the current for period, the average value of a current for a period is 0, but the average of the mean value of the square of the current mathematically is given by. And so if you want to know the average or the mean value of the square of current, it's mathematically normally given as, that is the root mean square. It is normally mathematically given as half that is relating in terms of their peak value squared, where we know that the I naught is the maximum or the peak value of the sinusoidal alternating current. And so we know that now if we want to know the average value of the current, the average value of the current for the period when the period is 0. So let me just draw this. Now when t is 0, we want to know the current here. Basically, that's what we're trying to say. So the average value of the current for a period is 0, but the average or the mean value of the square of the current is mathematically given by this. Now, what it means is that the I naught, which we know is the maximum peak value of the sinusoidal current, is given by the class will end, then you join, please. I naught is equal to, that is the average of this squared, is equal to I naught squared all over 2. And this I squared is the same as the root mean square, just as I already read. It's the same as the root mean square. So now we can say that this is the same as the root mean square.